Hello, today we're going to talk about 8.2, and 8.2 is about exponential decay models. Yesterday we talked about exponential growth, today we're going to talk about exponential decay. An exponential decay function is f of x equals a times b raised to the x power. Now here your a has to be greater than 0, so the number being multiplied by the function, and b has to be between 0 and 1. So that number being raised to the exponent has to be a fraction between 0 and 1. And you know, if it's a fraction, it could also be a decimal. Right, so we're going to look at f of x is equal to 1/2 raised to the x power. So I'm going to have 1/2 raised to the negative third. You know, that means we're going to take the reciprocal and cube it. So we get 8. 1/2 to the negative second, take the reciprocal and square it, and you get 4. 1/2 to the negative first, you just get 2. 1/2 to the 0, anything to the 0 power is just 1. 1/2 to the first power is 1/2. 1/2 squared is 1/4, and 1/2 cubed is 1/8. Make sure that you know how to raise these fractions to exponents. So make sure that you know how to get all of these values. So we're going to sketch our graph, set up our axes, 3, 4, 5. Our highest number is 8. 1, 2, 3, 4, 5, 6, 7, 8. So our first point is -3, 8. Our next point is -2, 4. -1, 2, 0, 1, 1, 1/2, 2, 1/4, and 3, 1/8. And there's our exponential decay model. With our exponential growth model, it went in this direction. As our numbers increased, it exponentially got larger and larger and larger. This one, as our numbers increase, our values are getting smaller and smaller. It's decaying. And the decay model is y equals a times the quantity 1 minus r, all raised to the t power. You should notice that that looks extremely similar to your exponential growth. The only difference is instead of a plus r, it's a minus r. So a is still going to be the initial amount. R is still going to be your rate, and don't forget this is a percent decrease, and that's going to be as a decimal. And t is time. That quantity, 1 minus r, so that quantity inside of those parentheses, is called the decay factor. Alright, just like our exponential growth, the exponential decay has a lot of real-world application. Our first example is there are 40,000 homes in your city. Each year, 10% of the homes are expected to disconnect from the septic systems and connect to sewer systems. So we've got 40,000 homes. That's our initial amount. We've got 10%, and that's 0.10 as the decimal. We want to write an exponential decay model. So we've got y equals our initial amount of 40,000, 1 minus our rate, and as a decimal, all raised to the t power. Just like with exponential growth, we're going to simplify what's inside those parentheses. So this becomes y equals 40,000 times 0.90, all raised to the t power. Estimate the number of homes using septic systems after 5 years. So we have two variables. We have y, which would be our total amount left, and t, which is the number of years. So we're going to replace t with 5. So we've got 40,000 times 0.90 raised to the 5th power, and you get 23,619.6. And so we're going to say that's going to be about 23,620 homes. Alright, flip your papers over. Next problem. You buy a new car for $24,000. The value y of the car depreciates by 16% every year. So we've got our initial amount of $24,000, And we've got our decay, how much it's decaying, which is 16%, which is 0.16 as a decimal. So we've got y equals 24,000 times 1 minus 0.16 raised to the t power. We simplify this inside piece to get y equals 24,000 times 0.84 all raised to the t power. So there's our exponential decay model. We want to use the model to estimate the value after 2 years, so we're not replacing our y, but we're going to replace our t. So we've got 24,000 times 0.84 raised to the second power, and we get $16,934.4. Now we know we're talking about money here, so even though our calculator only tells us 0.4, we know that when we write this, it becomes $16,934.40. Make sure that you're looking at the units that you're using and you write it correctly. Next one, estimate when the car will have a value of $12,000. So this is going to be the new car price, which means that's going to represent our y. So we've got 12,000 is equal to 24,000, the initial amount. Our decay factor is 0.84, and we want to find that t. So the only way we know how to solve this as of right now is to solve by graphing. And we know that we're going to put the left-hand side of our calculator into y1. We're going to put the right-hand side into y2. So left hand in y1, right-hand side in y2. Let's look at our calculator. Okay, so you see that we have 12,000 in y1, and you see that we have the 24,000 times 0.84 raised to the x power in y2. Now we also have to change our window. We normally start with a standard 10 by 10, but clearly if we're looking for a horizontal line at 12,000, it's not going to fit. So I hit the window, and I raised mine to 25,000. We know that our function's starting at 24,000, so I went a little bit above that to kind of get a better picture of what it's going to look like. And I am going to change this back to 10, and we'll see if we change it, we'll change it back. So we hit graph. There's our horizontal line at 12,000. And then here comes our exponential decay function. Notice that it's getting smaller. So we are going to sketch what our graph looks like. We've got our horizontal line at 12,000. Remember, if you're solving by graphing, you have to draw the graph because that's the work. There's no algebraic work to show, so you have to show the graph that's showing your work. And we want to find where the exponential growth model meets 12,000. So we want to find the intersection point. Second trace. Number 5. Enter, enter, enter. And we get that intersection point. Our directions say round to the nearest hundredth. So 3.98, comma 12,000, which means it's going to take about 3.98 years. So if you buy a car for 24,000, think about this. You're buying a car for 24,000, in just about 4 years, you've lost half of the value of your car. Alright, and our last problem. Your car is now worth $5,000. You bought it 6 years ago, and you expected it to depreciate 15% each year. This time we want to find out how much we actually purchased the car for originally. So this is our Y, this is our T, and this is our rate. We're trying to find that original amount, that A value. So we've got 5,000 is equal to our unknown original amount, 1 minus 0.15 raised to the 6th power. So we got 5,000 is equal to A times 0.85 raised to the 6th power. So if I want to find that A value, I'm multiplying it by a 0.85 raised to the 6th power. So to get that, I'm going to divide each side. And I would not round here. The more you round, the farther your answer is going to be off. So when it's a simple problem like this where it's just dividing by one piece, don't round until the very end. So A is equal to 5,000 divided by 0.85 raised to the 6th power. And we're going to get that that's going to equal about $13,257.34. Okay, and that is all for your exponential decay models.